All right, good morning or good day, everyone. Thanks for joining today's webinar. Sendo Reliability has this monthly series, and I've also just started a series, or we're experimenting with what we call a roundtable. And on February 19th, we're going to do an open discussion. And for the moment, I'm absolutely drawing a blank on what the topic was. Oh, I remember. Carl Carlson and I were talking about the the work many of us do within our own organization is often very similar to being a consultant and working to influence outcomes or help people understand the results of testing or risk identification and so on. In many ways, you're working like a consultant. So take a look on the live events at Ascendo Reliability. And if you're a member of the site, it's an option for you to join us for that discussion. It's usually a much smaller group, and we open up the microphones and it's much more discussion. So hopefully you can join us for that. But today is about accelerated life testing and test planning. And I think I've got most of the housekeeping type stuff done. And John, and I've got your notes on types of things to do. I'll take a closer look at that and most likely add some of those topics to future webinars and other stuff that's available on the Ascendo Reliability site. And let's see, one other bit of housekeeping. I've got a few links and information available just to the right of the rotating slides. Bring that back up again near the end of the presentation so you'll be able to click on those and get the slides if you want to, and plus check out some of those other links. So let me bring up the slides and we'll dive right into it. Um, so accelerated life testing is a pretty clear acronym in my mind. It's where we want to know how long something will last. And we often get asked that question as reliability professionals when there's about 3 to 6 months left in a program. We've got some working prototypes, and somebody hands you one of them and says, "So, how long will this last?" Or they may phrase it as, "Will this last long enough?" Or, "What's our risk and warranty? What's our expected failure rate going forward?" Um, and it can be phrased any number of different ways. But it's one of those things that we're trying to compressed time would be one way to phrase it, or cycles, or whatever it is that we're evaluating. Solar panels, for example, they're expected to operate with some efficiency for 20 years. Well, we don't really have 20 years, and we don't have a lot of history with solar panels with today's technology that have been operating for 20 years. So it's hard to know what all of the different failure mechanisms are and how many are expected to survive based on field data. So we spend a bit of time in the lab and with our chemistry and physics friends and so on, and we sort out how can we accelerate the aging process uh, for these, say, solar panels or whatever it is, and say within a year be able to make a reasonable conclusion about how many will survive 20 years. And that's what I mean by accelerated life testing, and I think that's a fairly common understanding. If you have something different, a different thought about what ALT is, please let me know. But hopefully that's pretty consistent with what you understand too. Now, the notion is that for businesses in our development teams and our plant operations, we're all trying to understand what's going to happen next week or next year or the next 10 years. We need to stock reserves for the warranty performance, or train and set up repair facilities, or we need to buy enough spare parts, um, all of which may take some time to do. And we don't want too many. We also don't want to have run out of parts, for example, and not be able to keep our system running. So customers want to know what kind of repair performance they have to perform, how long will it operate as expected, in many different circumstances. But also we want to know is, will this 100,000-mile warranty on our vehicle powertrain, is that a business, it's a business decision, and is it a good business decision? Is it worth doing? Will we end up replacing vehicles one after another just shy of 100,000 miles, or will most of them make it and not have problems? So there's business connections to doing this stuff, but along with those business connections come all the constraints. Uh, I was asked one time to do an accelerated test, and we needed answers really quick, like within the month. Uh, and by the way, we don't have any budget, and you have to do it yourself. There's no resources. We don't have chambers or anything like that. And then, I went back to my office and went, well, it's not a whole lot I can do other than create some random numbers and put it on a presentation. Uh, but we did some brainstorming. We figured out a few things, and but given a set of constraints, sometimes there's very limited amount of what you can do. And vice versa is that if you're looking at a program or supporting a team and understanding that estimating the future is pretty important, then planning ahead for the budget and resources you need in order to conduct an accelerated life test is a fairly prudent thing to do. Is you don't have to wait until it's late in the program and there's no money left to run a test. Try to anticipate uh, that we may have to do some testing and set aside some resources to do that. We might not have all the details yet, but we could certainly get it into the program plan and let the key decision makers know that this is part of what we're probably going to have to do in this program. But it goes cuts both ways. Those resources also constrain and sometimes seriously constrain what we have the options to do, what's possible. So when I look at running an accelerated life test, the these are really the four steps or four elements that I typically look at. And so this is really when I have worked with clients or have worked within programs and so on, I've been surprised over the years a few times. I've learned some things the hard way. I've also, I've talked to and worked with a lot of great people about the mathematics parts of planning, the the logistics part of the planning, the equipment and the systems that we need to use, but also just the practical, the practical side of what we're doing is it's something that we can get a number out of. We can create a simple basic test like this vice with crushing egg system here, and we could break a lot of eggs, and we could count up how many failed under different types of pressure. But is it relevant? Is it useful? Is it something that we really need to know and other people need to know? And is it helping us to answer business questions? Is what's the purpose of the test? Who's going to use this information? So keep this in context. If you're being tasked with uh, evaluating or setting up an accelerated life test, well, how do you how do you connect this to the business? And so I probably should have put 5 elements on here because I think that one's pretty important. We'll come back to it again, I'm sure. So anyway, I've got 4 pieces of information here or types of stuff that would help us then uh, create an accelerated test plan. And and I'm seeing a couple of questions here. Let me pause for a second there. But my thought here is that I'm going to talk about some of these elements that go into planning, and then we'll talk about some examples and see how to apply this stuff. So Shams is asking about relate test stand with product level testing. Yeah. So that's in the model part of this is how do you relate what you're doing to use conditions is the way I typically phrase it. Um, yeah, and looking at whether it's components or product hours or temperature or whatever it is, we'll talk about that briefly in the model section. Yeah, it, one of the worst ways to do accelerated testing is, um, I heard this phrase yesterday, is go kick a couple of wires in bundles of cables and see what happens. It's really hard to relate the benchtop exploration of what will fail, where the weaknesses are, with how long will it last. In some things, like drop testing, is really difficult to know how many times a customer will drop a product. But we probably can sort some of that out. And let's talk about that in one of the examples we got coming up. So some things are easy and some things are a bit more, take a little more creativity to make it happen. So the absolute number one essential thing, if you're going to run not just an accelerated life test, but I think pretty much any test related to reliability, is what's the failure mechanism? And simply asking that question also begs the question of, well, what is a failure? How do you quantify or characterize or identify something a customer would call a failure, right? If if the system doesn't start, if I turn the key on this Pinto and it doesn't start, if that's the only definition of failure that we have, then worrying about and testing the paint and the adhesion of the paint layers uh, and the protection of the metal from rusting is pretty irrelevant. But if we're also looking at the criteria of customer satisfaction, that the paint should survive for some period of time, and we're exploring different painting techniques, for example, well, how do we know it's failed? Is there a 1 millimeter square spot of rust? Is that deemed a failure for a door panel, for example? Or is it something more like this photo where it's the entire panel is devoid of paint and rust is blooming throughout it? Or somewhere in between? How do we quantify what is, and it sounds like a simple question in some cases. If the car doesn't turn over within a few seconds, while there could be many different reasons for that occurring, it's from a customer's point of view, it's what we would call a failure. But it gets grayer area is, well, how the paint job doesn't affect the motor starting. So it's a different set of criteria. And so you could use this car analogy, and yeah, and somebody call in and their line came in live. So I don't know what that was about. But anyway, uh, the notion here is there's failure modes, things that customers would recognize in the symptoms of, say, the car not starting or the paint peeling on the vehicle. But then we get into, well, what exactly is going on there? So in the paint element of it, it could be a chemical reaction, it could be a UV degradation, it could be a contamination that occurred prior on the metal surface prior to painting. It could be um, any number of different ways that the paint would fail on a vehicle. And so there's some chemistry going on there, right? There's some elements of UV interaction with the molecules within the paint structure and breaking it down, or the adhesion layer with temperature uh, coming apart and separating and so on. Or it could be a sequence of events that occur. But if I want to accelerate the failure mechanism of this paint failing, do I need humidity or UV radiation, or do I need mechanical defects that occur, say gravel chipping the paint in spots that propagates then into a complete failure? What's the sequence? And that really goes back to, one is we have symptoms that we classify as a failure, but then what's the chemistry and physics that really relate to it? So I'll just do a simple thought experiment here is, if you take a look at think through the different experiments that you typically run for your program. whether it's a new product development or it's a piece of factory equipment and you want to evaluate, say, a new vendor. You run it through its paces. And we could do a sequence of different styles of tests and explore all kinds of different stresses applied to the product. But how many of those have that story behind it that connects it directly to the failure mechanism? How many of you have heard of, or worse, I should say, you don't have to answer this question, but how many of you have conducted an 85-85 test? 85 degrees Celsius and 85 percent relative humidity for some duration of time. I've seen different standards that have different durations. Is, is anybody familiar with that test? You may not want to answer because of the way I prefaced it, but it's a mix of people that aren't familiar with it. So maybe we're getting past this notion of just running. This has been a standard test since the 70s of looking at various products and adhesions, especially in electronics. And it might be called HAST or it might be called a number of different types of tests. Oftentimes it's run at high temperature, high humidity, or run in, and it's oftentimes used as just a standard test. 85-85 for 168 hours with the magic number of samples in it. And you're looking for something that would happen. But let's say I've got a vehicle and I expose it to 85 degrees Celsius at 85 RH and say it's this panel, this hood, and the paint job that's on it. What would I expect to occur in 168 hours to this metal and paint? Not a lot, right? Now, if we know that the failure mechanism is moisture and temperature driven, we may start to see something. And maybe using higher temperatures and humidity or longer periods of times, we may run it longer. But yeah, John, and I've seen this oftentimes as a qual test. Yet I don't know of any place in the world that sees 85 C temperature ambient air. So it accelerates it to some extent, but what does it accelerate is really my point here. If I'm going to run any test of any kind, it's really focusing in on what exactly does this stress do to the molecular structure of the product, whether it's abrasion or chemical deposition, buildup, or contamination, or uh, motion from thermal cycling or physical motion, or run down the list of all the ways that our products can be stressed to failure. But somewhere in that mix is a failure mechanism, a breakdown of a polymer, a loss of adhesion, a chemical change, or a physical abrading, or something. So take a look later today, look through the sequence of tests that you've got either planned or are already conducting, and write down what failure mechanism or mechanisms that specific test is actually looking for. And if that's a difficult experiment, well, then you've got some homework to do because the test has got to have a connection to something that actually changes the product in order for it to be useful for an accelerated life test. And sometimes we know exactly what the mechanism is. We find it through failure modes and effects analysis, engineering judgment, field failure analysis. We do prototypes and we do halt testing. We find things that fail. And then we understand the failure mechanism through failure analysis and other engineering experiments. And then at some point, somebody says, well, given this barrel cracking in this via through thermal cycling, how many cycles before it cracks? And there you have a viable start to an accelerated life test. That's really what I'm driving at here. So there should be a story of what's the failure mechanism and how does that lead to a failure. That's really step one. So step two is then how do I relate that to the use conditions? And I think, I'm not sure who asked that or mentioned it earlier, I think it was Sean or Shans, but the notion is that if I run, for example, my poster child of a test that's not terribly useful, the 8585, is how do I convert that for my specific failure mechanism from those accelerated conditions to use conditions? Now, there's lots and lots of ways to do this. There's the simplest one is for example, an abrasion type process on, say, a brake pad on that Pinto car image I had earlier. Is with every cycle of braking, that brake pad, and it's by design, abrades a little bit. It wears. And when it gets too thin, it loses its ability to effectively cause braking. And so there's a little device in there that warns the driver that the brake pad's getting too thin. So performing normal maintenance on a vehicle and replacing the brake pads um, maintains that mechanism for braking. But the mechanism is that there's this metal on metal or this brake pad on the brake drum that creates friction that creates the braking forces. And that very same model was used with a product years ago I was working with that was a tape drive. It was a backup system for server systems to back up data onto tape. I don't know that we're using that anymore, but one of the things they found was that the distance between the tape and the read-write head, which was separated by a piece of glass, had to maintain a very precise distance in order for this system to work effectively. And they were able to work out a per meter of tape run over the head of the read-write drive would thin the glass, would abrade the glass a specific amount. And so per 1,000 meters of tape, they could measure how much abrasion there was. And so they could calculate how long before they would have to replace that read-write head in order to maintain the separation of the tape to the mechanism at a proper distance. And so their model was built off experimental work and measurements to relate the number of feet traveled or number of meters traveled of tape over the head to the thickness of the system of that piece of glass. But that was took some work to create that model for their specific system. Now, if they changed the tape or they changed the nature, the composition of the glass that was used as the barrier, they would probably have to run those experiments again. But they were able to create that correlation and thus had a model for their system. And it was actually pretty accurate. They ended up with lots of good field data and looking at correlating the actual use to their lab use. And that one was pretty simple, straightforward. But there's other cases where, like a chemical degradation of, say, that paint. Well, what's the model there? Now, if we know the chemistry, let's say it's a chemical breakdown of the polymer bonds within the paint structure that creates that adhesion, if that breaks down through UV radiation, there's a chemical equation for that. And we may be able to use Arrhenius equation to use temperature or some amount of energy to to create a model there. In other cases, it's much more complicated. Solder joints, for example, have all kinds of exotic different ways that the people have looked at those over the years and down into the molecular structure of these of the lattice of metals and in the formation of cracks and tin-rich areas that create embrittlement and so on. So in those cases, folks like Norris Landsberg uh, did a bunch of empirical studies looking at different thermal cycling profiles for solder joints and then created a model that described the time to failure behavior of those solder joint cracking failure mechanisms. Now, the Norris-Landsberg equation is specific to types of solder, different type structures of solder, and it's empirically driven. But whether I'm doing it on just the frequency of motion or creating a correlation of the amount of wear per cycle or analyzing many different experiments of thermal cycling on solder joints or using a physics of failure model that it goes into much more detail. And my little animal wants to say hi here, so pardon the background. He seems to be wired to my microphone somehow. But the notion is that once I know the mechanism, then there's probably a good bit of literature, either existing or something you may need to create that model. So if I'm running a test at a specific set of acceleration, then how do I translate that back into use condition? So the idea is that the mechanism helps you then find the appropriate model. And some models are straightforward and simple, like and others become more complicated. But without the ability to translate it, then I suggest you're really not doing accelerated life testing or modeling because you don't have an ability to convert it to use conditions. So as you're setting out to plan an accelerated life test, it's look at, well, what's the mechanism and how do I translate this? How do I convert it from stress conditions to use conditions? And, but there's also the notion here of, well, we've only got a limited amount of resources and probably a whole series of constraints. And the notion is that we may not have enough room or enough samples, and so what can we do with that? And so one option might be, instead of testing 30 units to create a reasonable time to failure distribution estimate, we could use the samples and run them to failure and do detailed failure analysis periodically, measuring performance over time and use a degradation test and maybe extract a little more information out of it, if that's possible, if we have a degradation type performance. In other cases, we may have to use, instead of an entire system, we may have to use a surrogate, a subsystem, or a sample of the material. So like that Pinto, instead of using the entire car and the heat profile of the engine underneath it with actual engines and outdoor evaluation of the paint job, we may have to use paint samples produced in a similar fashion as the painting process, but then using laboratory equipment and other systems to replicate some of the conditions that we expect would age that particular paint sample. It's a whole lot less expensive to get samples sometimes. The trick is, though, that it has to be relevant to the use conditions, to the actual conditions. Ideally, you would get a couple thousand vehicles and park them in different and operate them in different parts of the world and measure them. Uh, yeah, the minimum number of samples, Ravi, is in practice, it's as many as you can get. In theory, whether it's a Weibull distribution or a log normal or whatever distribution of time to failure that we expect to witness, we can back calculate out the samples. Or there's a variety of different algorithms based on what we already know about the failure mechanism that will give us. In some cases, though, we have a decent model. We know that it follows a particular wear out mechanism and so on. And we only need a couple of samples to show that we're either on target or better than the previous one. It's not an ideal situation, but there are a range of different ways that we have to deal with the resources and constraints we get to But the further we get away from actual customer use, and we step back to the lab, and then we step to samples, and we step to very few samples, and coupons, for example, the more risk we're taking that the testing won't translate well to the actual conditions. I once asked Wayne Nelson, how do you design the perfect accelerated life test? And he said, well, ship all of your products to your customers, let them sort out what exactly fails and when, collect all that good data, and then you'll have all of the information you need in order to design an accurate accelerated life test. Well, we almost never have that. We never have that information, or we have it very erratically and sporadically and kind of cloudy, misty looking into what is actually occurring. And so engineering judgment and good science come into play to help us understand what are the things that make the most sense for us to characterize and understand and run those tests. And yes, we're going to have to make assumptions and make some guesses as we design a test. And I, the only recommendation is that given the set of resources and constraints, is make as few assumptions as you can get away with, and then be clear about them. What's the impact of those things? So technically, you could run an accelerated life test in relatively short time with a handful of samples if you're comparing that against a body of work and a good model to show that you're at least a certain level of reliability at a certain time. But barring those models and understanding of the failure mechanism and character and so on, it may take a lot of work, multiple stresses, and of running them out to failure with enough samples that you get a reasonable estimate of the life distribution at different stresses. So then you can create a model relating time to failure to use conditions. So there's so many different ways to approach and attack these things. But when you start throwing in all of the constraints that come usually with actually trying to run a test, that's where our creativity has to play a role. But the guide is minimize the number of assumptions. Is within the sets of resources and constraints, the more exotic or creative you get, the more risk you're adding to the process. And the chance of getting a number that's fictitious, that doesn't represent the future, goes up. And oftentimes when we're pushing a test at the absolute minimums and keeping costs to an absolute minimum, we're not even able to determine if our number is fiction or not, and until the customers get it. And so there's a notion that I've heard called a few times type 3 error. And I'm sure you're familiar with type 1 and type 2 error from statistics, the consumer and producer risk numbers for looking at the confidence and power of your, say, a hypothesis test or evaluation. So anybody hear of the type 3 error? Probably, I'm not sure if I've written about it or not. I probably should. It's doing exactly the right, doing a test exactly perfectly, running a perfect experiment, but on the wrong question. And so it's the error is that the question is not relevant to what you're trying to explore. Um, yeah, and so part of this is the notion that if I if I'm running a test and I don't have a good story of the failure mechanism and clear understanding of how it fails, I may be running a test exactly to the book, exactly to a standard or to previous work. And let's say it's a water dunk test and we're checking for water resistance, for example. If I dunk something in some water and pull it back out, shake off the excess water and turn it on, see if it's still working, I may have looked for a failure mechanism related to immediate shorting and destruction of the circuit. But a week later, it had time for the corrosion elements to occur and to create shorts that only occurred during corrosion. And so while it may pass that initial experiment and come back out of the water and work just fine, a week later they all could be failed. But the test was, if it's evaluating just the immediate performance, then I have a type 3 error. I'm looking for the wrong thing. And sometimes we know what it is and sometimes we don't. So it's like the type 1, type 2 errors. There's a chance we could get it wrong. And this goes into how do we adapt our testing to the resources and constraints, but keeping an eye on that we still have a relevant test that is meaningful for us to make good decisions based on. And then there's the thought of the stress application. And I'll just be brief on this one because I think this one's pretty obvious. If if I have something that it flexes, for example, I worked one time on a product that was an implanted defibrillator that carried a bunch of capacitors, and when it sensed your heart, the patient's heart, going into a condition that required an electric shock, basically to bring it back into a normal rhythm, the function of defibrillation, it would discharge those capacitors. And um, the thought was then it would give you that defibrillation uh, earlier than a patient then would normally get it if they were, even if they had a defibrillator, external defibrillator nearby. So it would be an immediate application for high risk patients. And the basic idea is that, well, let's see if I can get a drawing here. So this, get my pen. So it was a cylinder and it was implanted in the chest cavity of a patient. And so each of these little cylinders carried, one of them carried the electronics and sensoring equipment and so on, and a bunch of others carried the capacitor pieces. But they needed it to be flexible. Just sticking a long, say, a 10 centimeter long metal rod inside your chest cavity uh, would probably cause more damage than good, just as the person was breathing or moving and so on. So these are titanium cylinders, and what they created was these little baffles. So this folded set of titanium that then allowed the system to flex in any direction. And so the question is how many times can you cycle this and flex it before you would create a fatigue failure in either the welds or in the baffles of these elements of this structure. And they knew how often a person was breathing per minute, for example, and the type of motion that that would create on this structure once it was implanted. And so they knew how many tens of thousands or hundreds of thousands, in some cases millions of cycles that it should survive. And so their relationship then was that they created a simple fixture that flexed these things fairly quickly. So they were compressing the frequency of the flexing and careful not to create too much heat because doing it slowly would not create that excess buildup of heat. And ran a bunch of samples to failure and counted how many times they flexed. But what they did initially was they flexed it to a much greater degree, thinking that that would be an accelerant in addition to just the number of cycles per minute. And they ended up with a number of failures that when they ran samples under a set of conditions that were closer to how it would actually flex, they didn't see. They completely changed where and how the thing failed. And so as you apply the stress is try to think through and make sure that it's related to the actual use conditions as close as possible. And as every level of acceleration you apply or type of acceleration you apply, that it translates to creating the type of failure mechanism, the exact failure mechanism that you're interested in. that is relevant for your use conditions. And that comes into the play my favorite was an ad for car doors being cycle tested by a robot. Well, a robot is not like my 8-year-old son when he was hanging off the door. And so the different loads and different approaches and different cycles and the different amount of debris and dirt and so on that build up on the mechanisms was not being replicated by this robot in a very clean laboratory. And so the relationship of that applied stress may be useful for some specific application of a specific failure mechanism, but it certainly is not applicable to all of them. And so which one are you trying to work with? Which one are you trying to evaluate? And so think through how you are applying the stress and how does that mimic actual use conditions or translate from the acceleration to creating the specific failure mechanism that you're looking for. So let's take a look at a couple of examples. Well, there's tons of other considerations, but I'm going to dive into a couple of examples here and ask some questions. So I didn't use pictures of the exact products I've worked with in the past or have these hypothetical things here, but I've got 4 examples of different ways of things can fail in different circumstances. And let's take a look at how we would go about setting up an accelerated life test. So this image I found online is of some tube and it shows some wear, which is relevant. This is the type of wear that this actual product saw. It was a very small grain of wheat size titanium cylinder, and it was on the end of a mechanical, um, some banded wire that had some flexibility. And it was a medical device and it carried some radioactive material and it was carried in a shielded area. And then during surgery, the surgeon would release this radioactive cylinder to the point where it needed to provide the treatment. And it would be for some duration of time, and then it would be retracted back into the shielded area. And for some reason, the design of the product had a curve or a radius that this cylinder had to traverse. So it was going down a tube basically. And as it did so, this one side of the product would wear. And there was a weld there that closed the cylinder and encapsulated the radioactive material. So the question was, well, how many cycles can this thing do before it wears this cylinder too thin, thus exposing the radioactive material in places they didn't want it to go? And well, it's a pretty basic task is get a couple of these devices and the types of material you're using and run the cylinder back and forth a bunch of times and then measure it. But how would you measure this? This thing's the size of a grain of rice and it's titanium. Any ideas on how you would measure this wear? The thickness is what we're really interested in. To a critical dimension is what they're considered a safe minimum thickness. How would you measure something relevant here in order to conduct this experiment? Run to failure, yeah. And we didn't have to load these with radioactive material to run the test, so it would be safe. Yeah, so we know the basic thickness. We had some tolerances on that. We know the basic thickness. There was a bit of variability on the weld, but with some cross-sectional work and characterization, they knew the thickness of that area. But it's not something we're going to get out a tape measure and measure. How would you measure this? This is one of those details. It's a constraint that we're dealing with is that um, we don't want to have to cross-section a bunch of different cylinders and then make the measurement. But we wanted to measure something that gave us a prediction of cycles to failure. Yeah. So we started with I don't know, they had a dozen or so of these different ones, and we knew the outside dimensions of this. And we had a pretty good idea from previous work of what the total dimension was. But what we really wanted to know was the rate of wear per cycle. And so they used an atomic force probe, atomic force microscope, essentially, that probed the profile of the edge of the cylinder. And so they used a mark and an indicator to always line it up the same way in the measurement system. And so what the probe did is it started here on the outer surface where there's no wear, and it created a profile of that edge. And so think of it as um, that initially it might have looked something like this with the weld on it. And so we were able to create a profile, a drawing basically of that dimension, and use this outer surface here, this centerpiece, as a datum point. And then as this thing weared, then it would slowly get rounded off. And after another couple thousand cycles, it would get a chamfer to it, is where it was seeing the wear. And by measuring the number of cycles to the distance worn away, we're able to create a relationship between the number of cycles to the rate of wear. And then you can work out the math to create a basic idea that per cycle it wears so many, uh, uh, a certain dimension of material gets abraded away. And then you use that to then predict how long before it gets to the minimum thickness. Yeah, and it wasn't linear, not at all. So we ended up with, I think, a dozen different sets of readings on about 20 or so different systems and created a model that then tracked the behavior. Because as it got flatter, it slowed down in the rate of wear. It had more surface area, and it was becoming the shape of that was minimizing the wear. And so it was an interesting phenomenon, but not a difficult one if you had the data. So it was an interesting way to do that. All right, so let's take a look at the next one. So I always love this example because it's the only time I've been handed an accelerated life test where sample size was not an issue. So in solar panels, in solar fields, there's a bunch of cables that connect the panels together, and it brings the power generated to an inverter and then off into the power grid. Those cables get attached to the back of these panels in the frames of these panels in many different kinds of ways, but one of them is to use these little plastic zip ties. And the ones they actually used were black because they had some UV um, protection material in it and were outdoor rated and so on. But there were three different vendors. And the question is can you run an accelerated life test to figure out which of these three vendors provides the best zip ties that are able to maintain a particular amount of holding force for these cables? Because when it gets windy, these systems vibrate, and so it loads these cables. And when the zip ties fail, it puts undue pressure on the couplings, the interconnects, and they're trying to minimize the cost of the connectors because there's thousands and thousands of these being used. And if they're held in physical location with these ties, then there's no problem. But if you lose enough of these ties and then you have the vibration from wind and other loading, those connectors come loose. And then you send out a technician to go reattach these cables. And that tends to be expensive for something that really shouldn't be happening. And so the question is here's 10,000 samples of each of these zip ties. How would you test this? What's the biggest constraint in this kind of an example? Here I got plenty of samples. I know that it's a polymer, pure polymer based system. It's temperature, humidity, UV to some extent. These are the kinds of stresses we're dealing with. So we could probably get a chamber to age these things fairly easily. And so let's say we solve the problem, we know the chemistry, We know it's temperature related, and we can degrade these systems perfectly well. But like the last example, how do you measure this? How do you measure, short of connecting these to cables and waiting for the wind to kick up? Yeah, I think you're on to the idea there, Myron, is that we know that as the cables degrade, their ability to not fracture is reduced. So think of it as a stress strength type of calculation. We get a pretty basic idea. We could measure how much loading these things would see. And Scott, that's what we ended up doing is we used a tensile test. So we took brand new systems and we measured, I don't know, 30 or 40 of them, and we got a profile of their strength for tensile because it really was the tensile loading of these things that caused their fracture. But as they degraded, small cracks would appear, a small embrittlement would occur within the polymer system so that as the stress of the loading would increase, that they were more likely to fail. And so we aged a bunch for some period of time, and we used Arrhenius's equation based on the chemical reaction of the polymer breakdown. It's called scissioning. Scissioning. I'm not able to pronounce that word very well, but it's a breakdown of the molecular chains within the polymer. And we know what that chemical reaction is. We knew the activation energy. And then we ran these tests at an elevated temperature to age them to say 5 years. And then we ran a bunch of tensile tests again. But running a tensile test takes time and technicians. And so we weren't able to test 10,000 of these things in any reasonable time. We were constrained just by our test facilities. Uh, Luckily, it wasn't that bad, so we were able to really get a bunch going here. But you can see that we had the failure mechanism was a chemical breakdown of the polymer. And working with chemists for that system of polymer, we knew we could determine the activation energy. And so we had a model to relate the application of temperature to a use temperature. And then we used the stress strength type calculations to look at the change of the strength of these systems as they aged, and then related that aging process to their reduction in strength. And so it was one of my favorite tests because we had so many samples. Of course, it wasn't perfect. We weren't able to test as many samples as we wanted, but it's the only example I know of where we had more samples than we knew what to do with. And we turned out that all three vendors were actually pretty similar. So they went to the lowest priced one and they just planned on walking the line every now and then and adding, using more cables, reapplying these attachment devices every 5 years or so um, as a preventative measure from these things wearing out. But the testing gave them a sense of how long they would go before there was an increase, a significant increase in the risk of these things failing. So it was pretty useful in that regard. So one more sample here, and then we'll wrap it up. So I, I was looking with great interest at the iWatch when it came out and the different bands that they had available. And so let's say that we've got a friction and magnet based attachment for a watch band. How would you test that? And what do we need to know in order for it to be a meaningful test? So what would the failure mode be? What would denote a failure from a customer's point of view if my watch band failed? Yeah, if it falls off, right? If it doesn't secure the attachment, if the attachment fails, right? But what would the failure mechanism be, right? The failure mode is it's not working. So the magnet weakens, too much force, You've seen a couple of good ones here. So like the stress strength calculate, idea is that if you're wearing a watch and you brush against something, puts a load on that hasp, or if like my son, when he was about 2 years old, he grabbed my watch and just twisted it. And had a pretty good grip for being 2 years old and fractured the watch band. Um, these are different. Yeah, doesn't secure. So uh, doesn't have enough frictional force to hold itself. The magnet's not strong enough to hold it either with friction or with the magnet in addition. So each of these things then we could break down using, say, a fault tree analysis or engineering judgment to look at what exactly would cause a magnet to weaken, or what would cause how much force does this thing have to withstand, and how would that ability to withstand that force change with time. So if it's just a friction type fitting, a snap fit type of a device, it's probably going to wear per cycle of use. Or others might be through temperature or exposure to different kinds of stresses. But that's the process. The start is really what's the failure mechanism, right? But let's say we find that it's the number of cycles degrades the system, the mechanical uh, tolerancing, the dimensions change with use, and over time it becomes looser and looser to the point where the magnet's not able to maintain an adhesion. What else do we need to know in order for this to be a viable reliability test? Yeah, how it's used. How often does somebody take it on or off? How often does it go through cycles of those forces? Now, this is a consumer product, and short of following a bunch of people around with this new device to see how they use it, um, how do we do this? Well, part of it is imagination to start, right? Let's use some engineering judgment and work with that. How often would it be dropped, for example? And well, we can, on the back of an envelope, using that hypothetically, is we could figure out that, say, somebody puts it on in the morning, they wear it all day, they take it off when they work out at the gym, or maybe the iWatch is when they use it at the gym. Um, take it off for the shower, maybe. I don't know. Goes on and off, say 3, 4 times per day. We could figure out a rough average for that. And each time you handle the watch, you have an increased chance of it failing or dropping. And so, say once a week, it falls off. And out of the 20 or 30 times it's manipulated. Now, we know some people are more clumsy than others and drop it more often, so there's some variability there. But very quickly, we could start imagining the different distributions and we could come up with worst case, nominal, and best case, and start creating some assumptions that you then could go out and measure and analyze and find more data on it. But the idea with this one is start with the failure mechanisms, the failure modes really, then the failure mechanisms related to it, and then work out what you need to know in order to create a model or to identify one that works. And sometimes it does just take engineering judgment to start, but be very upfront of what the assumptions are that go underneath that, and then go measure the ones that you can, and then track performance and adjust as you need to. But the idea is that sometimes we're in no man's land, especially with new technology and new concepts, and we're forced into making basic engineering judgments and assumptions. Well, that's part of the game. It's part of what we do. Document them, make them clear, break them down into measurable elements that you can, if needed, go confirm it and work it out that way. But the basic idea, let me bring up the last slide here. I can get my cursor to work. is that we get asked to create all kinds of different um, tests in accelerated life test. And the test that we ran last week on the last model we worked on probably won't work on the current one. Something's changed. The chemistry's changed, the use patterns changed, the model may have changed, we may have learned something from the previous one and so on. But the basic idea is to start with the failure mechanism. What's the model? How do we translate this and how do we apply stresses in a meaningful way such that we then create a consistent story that we can explain very clearly and we can test and challenge and understand that it is the right model, the right system, the right test. And then I'll do all of this with no budget, on time, and understandable by the decision makers. So it can be a lot of fun. It can get deep into the science, which is, I think, the fascinating part. But it also can be critically important to the decisions you and your organization are making uh, for the products you're developing or the systems you're bringing online. So there's a couple of different ways to look at this. Yeah, and Ravi, it is a good way is to look at worst case, but then the question becomes, well, how many of our customers bang their watch into the railing of a staircase repeatedly as they walk up and down the stairs? If it was my 2-year-old son, it was probably all the time. But how many of our customers would be at that worst case? And do we want to change the design and modeling to accommodate, say, the 1 percentile that uses those extreme stress conditions? And so understanding the relationship of the stresses at multiple points, as in a model, allows us then to make those decisions. Are we designing for the 90th percentile of our population or the 99th percentile or some other fraction of people that we expect to see using it and under different conditions? If we just do a pass fail one style test and we don't end up with a model, it's very hard to make those business decisions and make those trade-offs. So it's all part of this accelerated life test planning. All right, so running a little bit over. Um, I think I've got 1 or 2 slides here. What I was going to do is let me leave the summary here up and I'll pull up the uh, downloads part so you can still get to that. May have moved your um, chat window on you there, so hopefully you can still find it. So I'll stay on the line if there's any questions or thoughts. And I know that there's a bunch more to this. John was saying right at the start is that, pretty much anything on accelerated life test would be of interest. So I'm thinking through some different um, topics and open to ideas of which we'd like to see in these webinars or from other material, which would help you to effectively design and run accelerated life tests. Yeah. So, Robbie, the idea of it being a failure is happening in your warranty period, if that's during use, um, well, that becomes pretty prominent for the business decisions real quick because that's real money going out the door. It also affects customer perception of the product. So it has a couple of downsides to it. But hopefully you can get some systems and get a good picture of what the failure mechanisms are and then connect your testing to that. That would be pretty essential. I just had a panic moment there. I did start the recorder when we started, so I'm good. I've done that before. I get all the way through this and then realize that I hadn't started the recorder. So, and if you joined us a little bit later, if you'd like to see this replayed, we're going to have it up on the Accendo Reliability site under the Accendo Reliability webinar series, which is also available on iTunes and Stitcher as a podcast. So if you want the audio only version to these podcasts, you can subscribe to it and put it into your favorite podcast player. Well, you're welcome, Philip. It's ALT is something that I mean we really should spend a lot more time talking about, and I agree with John that it's a big topic and lots of specifics in it. So hopefully a couple of things out of this were useful for you or confirmed what you already knew. So I appreciate everybody joining today. A session on Weibull, just the Weibull analysis for accelerated testing or just Weibull data analysis in general? You're welcome, John. Hopefully we'll come back and talk about this some more. As you can tell, I enjoy talking about ALT, and I've gotten to break a lot of cool stuff over the years. So Weibull in general, yeah, we can do that. So there's a couple of topics. And then let me open this up as people are signing off here. And Shams, let me take a look at your question. I did see it earlier, but it also was, yeah. So that one I'm gonna have to think about a little bit, Shams. So if you could send me an email with an outline of the question, maybe a little more detail, I'd be happy to comment on it. Um, let me drop my email in the box here. Yeah, just send me a quick note and we can take that offline, dive into it a little bit more, make sure I understand the question. Downloads are grayed out. Huh, I'm not sure what that's about. Uh, I'll add the downloads to the page where I'll have the recording. So it's going to be on, one way to find it quickly is go to reliability.fm, and that takes you to the podcast network page on Accendo Reliability. And if you look for Accendo Reliability webinar series, probably tomorrow, I'll have the recordings posted and available on iTunes, and I'll add the downloads, which is really just the PDF of the slide set. Yeah. So should be, oh, one way is make sure you select what you want to download. So if you click on the Create Alt Plan Slides PDF, then the download files should become available. All right, good. Thanks for all the help, everyone else. So any other topics? I'm in the process. I've got next month's webinar set up, and but I'm considering a number of different ideas, and accelerated testing seems interesting, especially to this group, no surprise. But I'll have to work in some more webinars on that. So a few reliabilities and exposure is less how do I improve? You know, Robbie, one of the things, and this is a complete tangent from today's topic, is during a conference in January, the Reliability and Maintainability Symposium, Celine and Adam and I were bouncing around ideas and we're asking how to best support reliability engineers when they're basically working on their own within a company. Huh, sorry about that, Philip. It should be PDF. I'll have to double check that. I'll make sure it's PDF on the website when I get it uploaded there. And the the idea came about of helping people get together into smaller groups, a system and a program called Masterminds, where say 4 to 6 people meet regularly and talk about what's working, what's not working, and challenges they got coming up. And so we're in the process of trying to figure out how to do that and help support reliability engineers into getting into mastermind groups. So it's different than mentoring. It's a small group of peers, not a one-to-one teacher mentor type package. But there's also different than forums and discussion groups where you might be 1,000 people and you don't really know them. So having an ongoing discussion with people you get to trust that are there really to help you solve problems is this idea of masterminds. And we didn't invent that. It's an ongoing uh, process that many different parts of society have got ways to find groups and get engaged. It's just that we haven't found one for reliability professionals. And so the idea is then to create a way to help us find each other and form these groups, and then provide some basic concept training and initiation and so on, so that you're more likely to be successful at it. But so watch for more of that. If you're a member of Ascendo Reliability, and or come back to one of these webinars, we'll certainly be talking about it some more.